Moving on, we'll look at some more factors that sort of set the stage for quantum physics, and then we'll full-fledged dive into it. So in the previous section, we just spoke about the energy emitted by a black body. So what is a black body? It is, in simple terms, a body that is a perfect absorber and perfect emitter, meaning it is any substance which absorbs 100% of the radiation falling on it and reflects back 100% of it. Meaning whatever radiation falls on it, it takes everything and reflects it back perfectly. That is a black body in ideal conditions. But again, in the real world, ideal conditions are difficult to create. Any body you see, any substance, no matter how smooth and polished it is, there are going to be impurities, abnormalities on the surface. So in practicality, we say it is a body that absorbs and emits most of the light falling on it. I think more than 85 to 90% of the radiation falling on it should be absorbed and reflected. I think that's the criterion for a black body. So how does it look? Generally, it's a spherical polished cavity, blackened inside and completely closed except for a narrow orifice. So this is what it looks like. The inner surface is completely covered with black paint, and there's only a small opening through which light enters and is reflected. That is a black body. So the other contents on this slide are, like I said, when scientists started working on these questions of energy and temperature, they assumed these are continuous quantities, and they performed some experiments and they ran into some mistakes, and that is when they thought, okay, maybe my assumption is wrong, energy is probably discrete, it's quantized. So what are those mistakes they made is what we're going to see in this slide. So firstly, according to classical theory is the opposite of quantum. Classical physics is the opposite of quantum physics. It assumes that a quantity is continuous. So according to classical theory, energy is related to amplitude and not frequency. So when an object moves, when there is a change in motion, that is when something which is in rest starts moving, or when something which is moving slows down and comes to rest, or when a moving body accelerates or decelerates, that is when they assumed energy should be given out. But what they experimentally found out was that under thermodynamic equilibrium, a particle can occupy a given energy state and still acquire or release a continuous range of energies. Meaning, so they assumed that energy is absorbed or given out only when there is some sort of movement. But experimentally they found out that even when a body is stationary, when it is staying within its own energy state, it is still able to give out or take in energy. So that was one contradiction they arrived at. The next contradiction was the UV catastrophe. So according to classical theory, radiation from a hotter body should have more UV rays than observed experimentally. Meaning, according to classical theory, they assumed that energy is a continuous quantity, and they performed some calculations saying at this temperature I should be receiving this number of UV rays emitted from my black body. But what they actually found when they experimentally performed was that the body emitted fewer rays than what they had calculated, which means there was something wrong in their assumption. So that is one more mistake one more, let's say, roadblock they ran into, which made them question their assumption that energy is continuous. And one last thing we look at in this slide is Wein's law. So Wein was one of the people who tried to give an expression for energy in terms of frequency and wavelength. So he tried heating a body at different temperatures and observing the radiation it emitted. What he observed was, as the temperature increases, the energy at each wavelength increases. The wavelength at which maximum energy is emitted decreases, and the total energy at a given temperature is proportional to T to the power m, which was later found out to be T to the power 4. But yeah, when he performed the experiment, he only realized that it is proportional to some power of T.